Good morning. Welcome to Smith and McEntie's latest film, BlackHoles, Cosmic Superpower. Narrated by David Attenborough. Produced by Smith and McEntie. A black hole forms in the final life cycle of a very large star. Seen here is a scale of just how large a large star is. Notice our sun on the far left. We think of our sun as relatively large, at least until we see stars such as Pollux and Arcturus on the right. These stars begin to synthesize iron just like supernova stars, but collapse into a singularity, or point of infinite density, at their death. This singularity is the heart of a black hole, and gravitates in a way only explained by Einstein's special relativity, but more on that later. This is an example of a very large star, very near collapse, Eta Carinae, very close to our own solar system. Perhaps when collapse is complete, it too will become a black hole. After this eventual collapse, the black hole begins to swirl as its gravitational field starts to trap all matter nearby, including electromagnetic radiation. This picture provided by NASA shows an X-ray image of a swirling black hole. These swirling black holes are known as unstable or oscillating black holes. According to Einstein's general relativity theory, they produce gravitational waves which disturb the universe around them. However, due to the very slight differential that these waves create, they have been extremely difficult to detect. However, they are best explained like this 3D model of a circularly dispersing wave which travels through the universe like a ripple of water through a calm pond. As an object is entrapped in a black hole's gravitational pull, it begins to experience time differently according to Einstein's special relativity, as it accelerates near the speed of light. Also, an object could not differentiate the difference in speed after its acceleration. Therefore, if Earth were sucked into a black hole, we would begin to experience time differently, even though there is no evidence to suggest our extreme velocity from a normal orbital spin. Logically, everyone is curious as to exactly how Einstein's special relativity applies to gravity, and why it differs from Newton's traditional definition. What you see here is the first page of Einstein's mathematical equation to explain two-dimensional gravitation. It requires some of the world's largest supercomputers to generate any type of worthwhile data, so we have cherished our ignorance of this astrophysical property. Assuming that you could actually get this close to a black hole, the ball in the center of the yellowish area theoretically represents the singularity of the black hole. This is the point of supposed infinite density at the heart of the black hole. This is the cause of the gravitation towards and through the spiraling black hole. Now that you've finally reached it, you become spaghetti. Yes, spaghettification is the coined term suggests the rapid thinning of your now ductile form, which would occur in the pressure of the strongest gravitational force in the universe. Now wrap your brain around this. The Milky Way, our galaxy, shown here, looks ironically like a picture of our other swirly black holes. That is most likely because there is a massive black hole at its center. Recall if you were being sucked into a black hole. Well, we are. You would begin to experience time differently but never know it. Strange. Ironically, our fate is inevitable, as the gravity of black holes does not even allow electromagnetic radiation, i.e. light, to escape. There is no possible chance of evading our eventual fate. Now that we all understand the essence of black holes, it's time for the weird part. Wormholes in parallel universes are some of the least understood phenomena in the universe. Albert Einstein and another physicist by the name of Nathan Rosen hypothesized that for every black hole there is another gravitational point, known as a white hole, or also known as a white fountain. These two points will be linked by some sort of dimensional bridge, or wormhole. Thus any matter swallowed up by the black hole will be quickly spat out by the white hole in an unknown location. This could be either a distant point in the universe, in which case a wormhole will act as a shortcut through space and time, or it could be a parallel universe, in which case it would act as a bridge between different dimensions. Mind-boggling, to be sure. This is a diagram of how you would ever survive a trip through a black hole, even if you could design a spaceship to survive speed of light travel, the rigors of spaghettification, and other space risks. It will be an interesting day when this comes to fruition. Good luck, and Godspeed.